Welcome to my 75th tutoring session in A-level chemistry. In this video, I'll explain the IR spectral characterization of aromatic compounds involving aromatic carbon-carbon double bond stretch, aromatic C-H stretching. And I'll also explain the isotope effect in IR spectroscopy involving the aromatic carbon deuterium stretching. I will discuss the IR spectral peaks of CH bonds formed by sp3 and sp2 hybridized carbon. Now, every bond in the molecule absorbs IR radiation at a specific frequency, and hence each bond gives an absorption peak in the IR spectra. When you observe the structure of benzene ring, you will find two types of bonds. One is the aromatic CH bond and the other is the aromatic carbon-carbon double bond. In case of deuterated benzene, you'll come across aromatic carbon deuterium bond and aromatic carbon-carbon double bond. So the only difference between the structure of benzene and deuterated benzene is that the hydrogen atom is replaced with deuterium. And let's see how this replacement of hydrogen with deuterium brings about changes in the spectral peaks of their respective IR spectra. Now here's the IR spectra of benzene and here's the IR spectra of deuterated benzene. Now the spectral peaks of benzene differ from that of spectral peaks of deuterated benzene. This is due to isotope effect. This is due to replacement of hydrogen with deuterium. Now the mass of the atoms decides the stretching frequency. And let's see how the mass of hydrogen and deuterium decides the stretching frequency for the respective spectra. Now the electronic structure of hydrogen, it has a central nucleus that contains positively charged proton with negatively charged electron orbiting around the nucleus in its respective shell or energy level. It is a lighter atom. It is the first element in the periodic table with atomic number 1. And how about deuterium? Now deuterium is an isotope of hydrogen. It has a central nucleus that contains one positively charged proton and one electrically neutral neutron with negatively charged electron orbiting around the nucleus in its respective shell or energy level. Now deuterium, it contains one additional electrically neutral neutron in its nucleus. So because of the presence of additional electrically neutral neutron in the nucleus, it is heavier than hydrogen. So deuterium is heavier atom as compared to that of hydrogen due to the presence of the neutron, which adds to the mass of the atom. Now the carbon-hydrogen stretch occurs at a faster rate. Now the faster stretching of the CH bond is due to the lightness of the atom, that is hydrogen. So hydrogen is a lighter atom and this leads to the faster CH stretch. And in order to match this CH stretching frequency, which is occurring at a faster rate, wave number of greater than 3000 centimeter inverse is required. So higher frequency is required in order to match this CH stretching frequency. And in case of carbon deuterium bond, it stretches at a slower pace. And in order to match this slow stretching carbon deuterium bond, a lower wave number around 2270 centimeter inverse is required. So to stretch a lighter atom like hydrogen, a higher frequency is required, while to stretch a heavier atom like deuterium, lower frequencies required. So it is the mass of the atoms which decides the stretching frequency. So lighter the atom, easy is the stretching. Heavier the atom, difficult it is to stretch. So let me draw a reference line at around 3000 centimeter inverse. Now this line, this reference line that is drawn at around 3000 centimeter inverse, it differentiates the aromatic CH stretching from aliphatic CH stretching. Now aromatic CH stretching, it occurs at wave numbers greater than 3000, while aliphatic CH stretching occurs at wavelength lower than 3000 centimeter inverse. And hence the reference line is drawn at around 3000 centimeter inverse. So in case of benzene, you find the presence of only the aromatic CH bond, and hence the absorption peaks corresponding to aromatic CH stretch occurs at around greater than 3000 centimeter inverse. So what about the deuterated benzene? In deuterated benzene, you don't find any aromatic CH bonds. You come across only aromatic carbon deuterium bond. So the carbon deuterium bond in case of deuterated benzene, it stretches at around 2270 centimeter inverse. Now this shift in stretching frequency to a lower wave number is due to isotope effect. This is because of heaviness of the deuterium atom as compared to the hydrogen atom. So when you compare and contrast the aromatic CH stretch to that of aromatic carbon deuterium stretch, you will find that aromatic CH stretch occurs at wave number greater than 3000 centimeter inverse, while aromatic carbon deuterium stretch occurs at wave number lesser than 3000. So it happens at around 2270 centimeter inverse. So this shift in stretching frequency from 3000 centimeter inverse to 2270 centimeter inverse is due to isotope effect. So deuterium atom is heavier than hydrogen atom. So it is the heaviness of the deuterium atom that leads to slow stretching, and hence the absorption peak for carbon deuterium stretch occurs at a lower wave number. And there is no aromatic CH stretch peaks in case of deuterated benzene, as there are no aromatic CH bonds. An aromatic carbon-carbon double strand stretch, you find it around the double bond region. While the aromatic CH bend, that is out of plane bend, is seen at around 674 centimeter inverse. An aromatic carbon deuterium bend, it occurs at around 500 centimeter inverse. Now again you find a shift in stretching frequency towards lower wave number. So aromatic CH bend occurs at a higher wave number, while aromatic carbon deuterium bend occurs at a lower wave number at around 500 centimeter inverse. So this shift in stretching frequency towards lower wave number in case of aromatic carbon deuterium bend is again due to isotope effect. So you find variation in the frequency and intensity of the peaks mainly due to isotope effect. Now here's the IR spectra of benzene, and here's the IR spectra of toluene, it's also called as methyl benzene. Let's examine the structure of these two compounds. So similarity between these two structures is the presence of benzene ring, and hence you will come across aromatic CH bond and aromatic carbon-carbon double bonds in both the structures. And one additional differentiating feature in case of methyl benzene is the presence of methyl group that is directly attached to the benzene ring. With the presence of aliphatic CH bond that is contributing towards aliphatic CH stretch. When IR radiation impinges or strikes the bonds of these two molecules, aromatic CH bond, aromatic carbon-carbon double bond, and the aliphatic CH bond, they stretch at different frequencies and hence they absorb at different frequency of incoming IR radiation, resulting in characteristic appearance of absorption peaks at respective wave numbers. So let me draw the reference line at around 3000 centimeter inverse. So in case of benzene ring, you come across the aromatic CH bond, and hence peaks at wave number greater than 3000 is due to aromatic CH stretch. So due to aromatic CH stretch, you see the absorption peaks somewhere between 30562 to 3091 centimeter inverse. And there are no aliphatic CH stretching peaks due to absence of the alkyl CH groups in benzene ring. So what about toluene? So in case of toluene, you find the aromatic CH stretching peaks due to presence of the CH bond in the benzene ring. And you see the aromatic CH stretch somewhere between 30282 to 3087 centimeter inverse. This is due to the presence of aromatic CH bond. And you can see that the aromatic CH stretch, it occurs at wave number greater than 3000 centimeter inverse. So you see the absorption peaks at wave number greater than 3000 centimeter inverse. Because both the compounds, they have a benzene ring with aromatic CH bond and aromatic carbon-carbon double bond. In case of methyl benzene, you find the presence of the methyl group directly attached to the benzene ring, and which contributes to the aliphatic CH stretch. An aliphatic CH stretch, as I've already mentioned, you see the absorption peaks at wave number lesser than 3000 centimeter inverse. And now you know why I have drawn the reference line at around 3000 centimeter inverse. Now this reference line at 3000 centimeter inverse is the line which differentiates the aromatic CH stretch from aliphatic CH stretch. An aromatic CH bend at around 674 in case of benzene, an aromatic CH bend at around 696 and 7 to 8 centimeter inverse for the methyl benzene. Here's the IR spectra of benzene and octane. So benzene is an aromatic compound, while octane is an alkane. It is a saturated hydrocarbon characterized by presence of carbon hydrogen and carbon carbon covalent bonds. So in case of octane, you find only the aliphatic CH bonds, and hence you find the absorption peaks corresponding to CH stretch somewhere between 2867 to 2969 centimeter inverse. And in case of octane, there are no aromatic CH stretching peaks, as there are no aromatic CH bonds in octane. So in case of benzene, you find the aromatic CH stretch somewhere between 30562 to 3091 centimeter inverse. This is due to presence of aromatic CH bonds. And there are no aliphatic CH stretching peaks in case of benzene, as there are no alkyl CH groups. Here's the IR spectra of methyl benzene, and here's the IR spectra of benzyl alcohol. Now, first let us consider the structural similarity between these two compounds. Both the compounds, they have a benzene ring characterized by presence of the aromatic CH bond and carbon-carbon double bond. These two compounds differ with respect to the side chain. So you find the methyl group in case of toluene, and in case of benzyl alcohol, you find the side chain, that is a methyl group, extended with a hydroxyl group. So in case of benzyl alcohol, you find the presence of hydroxymethyl group directly attached to the benzene ring. So reference line drawn at around 3000 centimeter inverse. So in case of toluene, you find the aliphatic CH stretch less than 3000 centimeter inverse. And you find the aromatic CH stretching peaks at wave number greater than 3000. So you find aromatic CH stretch as well as aliphatic CH stretch for both the compounds. So in case of benzyl alcohol, you find the aromatic CH stretching peaks due to presence of aromatic CH bond. And you find the aliphatic CH stretching peaks somewhere between 28672 to 2969 centimeter inverse due to presence of the methylene group, that is the CH2 group, which contributes towards the aliphatic CH stretch. And you also find a additional terminal hydroxy group attached to the methylene carbon, and you find the stretching at around 3326 centimeter inverse. Now the OH group, that is the alcoholic OH group, it stretches at a higher wave number because the OH bond is highly polar. It is polar as compared to the CH bond. And because of the increased dipole moment and polarity, you find the appearance of this absorption peak at a higher wave number. So greater the polarity of the bond, greater the dipole moment, and hence it absorbs at a higher frequency. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.